So here, in this animation, we have a source that's emitting sound, and it's moving. So I want to make a parallel because we did study Doppler effect once before in special relativity. So I'd love to, let's remember how Doppler effect for light worked. Okay, so for light, so remember that the frequency that we observed is the frequency that was emitted times 1 plus v over c all over this famous square root factor.
The gamma factor.
It's the gamma factor. So here, this v is the relative speed between the source and the observer. Okay? Now let's take a look at, this is for light. Now I want to give some thought to what it's going to be for sound. Okay. So now, here, our little pink dot here, this is an observer. And you can see that as the source goes by him, as he's coming towards him, he sees wavelengths that are much shorter. And then as the source goes away, it looks like the wavelength, the distance between the maxima, gets bigger. So, anybody want to give me a sound demonstration of what Doppler effect sounds like? Awesome. So, let's describe how this works. Okay, let's start off if we have a moving source. Okay, so let's draw some pretty pictures here. So at t equals 0, so we're going to have our source, and it is going to have emitted one wavelength. It's going to have emitted one peak. And that peak is going to be moving to the right with some speed v, which is the speed of sound. Okay? Now let's look at this. At some t equals the period, so the time between the maxima. And what's happened is that this guy, he's traveled a distance. But this guy has also, the emitter right here, he has also traveled some distance. So you can see that the distance between, this is what he emits, his next one. You can see that the distance between where the peak was at t equals 0 and where the peak is at t, what do we call that distance? Let's see. Let me give you a little, let's imagine that the source is not moving. Okay, if you have a source that's not moving, at t equals 0, he emits a pulse. At t equals t, he's still here. This pulse has traveled some distance and emits another one. What do we call that distance? Yeah, it's vt, but it's also known as lambda. It's the wavelength, right? Okay. But here, if your source is moving, and the source is moving with some vs, then that means the distance that the source is moving is vs times t. And let's see, the whole distance here is lambda, right? That's the lambda that was emitted at, that's lambda naught. So the new wavelength that somebody sitting over here, very happy listening for sound, the distance between the wave peaks that they're going to see, this distance, lambda right here, it looks as though, let's see, it looks like this distance lambda plus the distance that the source moved is equal to the original wavelength. Yeah? So it looks like it's equal to, let me write it this way. Let me write this distance is equal to lambda naught minus this distance. rate is really just the inverse of the frequency that we're emitting at, right? So I'm going to write this as 1 over nu naught. Let's see, and lambda naught is just the speed of sound over the sound that's frequency that's emitted. So it looks like we have something that looks like this. Okay, so that's all equal to lambda. Now, so let me simplify that. We have lambda, which is also the speed of sound over the frequency that the person listening hears, is equal to that. So it's V minus Vs over the frequency that was actually emitted. So that means that the frequency that the person hears, if we invert this whole thing, let's see, and solve it for V, it looks like we're going to get nu naught, and it's going to be what? V over V minus Vs. Did I get that right? These are nus for frequency. These are Vs for speeds. Is that not obvious what's nu and what's V? Here, I can put little capitals on here. Does that help? Okay. Oops, I left my remote. Okay, so up here on the visual, you can see it a little neater than I wrote it. Okay. Going through the same derivation, and we get that the frequency of the wave that we hear is changed by the speed of the wave over the speed of the sound minus the speed of the source.